Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed about the first order system and how we can study the first order system based on give different test inputs. We already observed that by giving different test inputs, how we can uh, study the ideality of the system, how it behaves when certain inputs are given, and how fast it is approaching the steady state value and other phenomena we have studied for the first order system. So today we are going to learn about the characteristics and other segments for second order system. So by seeing the second order system, we have the order of this second order and the characteristic equation which is quadratic. So let us analyze this in time domain. So consider a unity negative feedback system with open loop transfer function omega n square by s into s plus 2 delta omega n. This delta being the damping factor which we will see later on, and omega n is the natural frequency of this second order system. So if we consider a unity negative feedback system, which is being depicted over in this figure, and if we find out the overall transfer function for this diagram over here, we have the overall transfer function as g over 1 plus g. We have already seen that if it is a unity negative feedback system, where g being the overall transfer open loop transfer function, which is the omega n square by s into s plus 2 delta omega n. So if we substitute that in this formula, which is the overall transfer function g of s by 1 plus g of s, if we substitute g of s, which is this equation over in this g of s, what we have this. So by placing this g of s in this equation, we have the overall transfer function which we can write as omega n square divided by s square plus 2 delta omega n s plus omega n square. So if we observe the denominator polynomial in this overall transfer function, which is having the highest power of 2, so thus we can say that it is a second order system, uh, and the characteristic equation of this second order system is quadratic. So if we see this characteristic equation, which is the denominator polynomial quadratic, we can have a quadratic equation which is s square plus 2 delta omega ns plus omega n square, where omega n we already discussed that this is the natural frequency of the system and delta is the damping factor of this system. So if we kind of solve the roots of this characteristic equation, roots of this quadratic polynomial, then we can have the poles, the closed loop poles of this system. So by doing that, so how we can find out the roots of this equation, quadratic equation? If you have observed, you have the quadratic equation roots formula. By applying that and by applying the determinant, we can have different conditions. So minus 2b minus b plus or minus root of b square minus 4ac by 2a. If we apply that, so we have here a is equal to 1 over here and b is equal to 2 delta omega n over here. If we apply that, then we can have this. So if we solve the roots of this characteristic equation by using this formula, we can, if we simplify this further by taking 4 common with this root, and if we take out this from root, we can have 2 common over here. And if we cancel this with this denominator, we have the roots of this characteristic equation, which is minus del omega n plus or minus omega n into root of del square minus 1. So if we see that based on this expression which is in the root, we can have different types of roots. So if we have this delta over here, which is the damping factor, which is equal to 0, if we substitute delta equal to 0 here, we can have the roots as complex conjugates, because this one will become minus 1 over here, and square root of minus 1 will become the complex number j. So the roots will be of complex types. So if we have the delta is equal to 1 over here, we have the square root term got eliminated, and we have minus delta omega n, which is repeated roots for this quadratic equation. So based on this different values of this delta, we can have different roots. So if we have delta is equal to 0, then the roots are imaginary. We have already saw that. And if we have delta is equal to 1, if we eliminate this second polynomial over here, we have the repeated roots real, which are real and equal. If we have delta which is greater than or equal to greater than 1, so this term over here will become positive, and if you take a square root of positive, that will yield a real number, but they are not equal. And if we kind of adjust this value between 0 and 1, then we can have complex conjugate roots. So based on this delta, we can have different types of roots. We already saw that. So if we write this output equation, we can have this output equation over here. So the Laplace transform of this output is equal to this characteristic polynomial in the denominator multiplied with this input Laplace transform over here. So that's it for today, guys. In the next video, we will be learning about the second order system based on different test inputs. So thank you.